Bismillahirrahmanirrahim. Assalamu alaikum everyone. Today we would be performing our the Boolean function, Boolean expression with De Morgan's law. So for this, first of all, we would be seeing it on Proteus software and we will be proving them. First, we will go for run as administrator. The Proteus software would be open. So here my Proteus screen is open. I'm using Proteus 8.6 professional, and as I've already made these circuits, I'd be simply going on Boolean expression. That would be one of the tasks for today. So this is one of my circuit of Boolean expression, one of the circuits. The next one I would be proving in the next slide. So first of all, let's prove this one circuit. So I'll be playing it play. This circuit is playing right now. Now this circuit which is present over here, this implies for the equation that is given as a naught plus a naught multiplied by b naught plus c naught multiplied by d naught. Now this are AND gates. AND gates present as the equation of dot or multiply, and the OR gate implies as positive or plus or addition. So first, when both the inputs are 1, as a NOT gate would be producing them as 0, so this function would both the inputs AND gate would be 0. So low logics, and then this low logic would go from here to low logic input of this OR gate to one of them. Then the next, due to the OR function, we know that if any one of the logic is high logic, this will result in the high logic of the OR gate. So as both of them are low logic, as from this it is converted into the loss of it, or if we convert any of them, open any of them as 1, you can still see that the logic is low. The reason to this is because although the AND gate has or NOT gate has converted into the 0 into 1, but due to the OR AND gate function, if any the logic is 0, any of the logic is 0, as it is a multiplication function, the result will be a 0 or low logic. Now, if we close all of them together, or any one of them is completely closed, like this part, A and B both are 0, they will pass from NOT gate, and this NOT gate will invert them to 1, means high logic. In this high logic, when both of them are high logic, AND gates logic would also, output logic would also be high logic, which will result in the production of high logic at one of the inputs of the OR gates. When one of the inputs of the OR gate is 1, any one logic of the OR gate is 1, it will reproduce into the high logic of this expression. So by this expression of Boolean function is being proved. And we open this and we do this, that this is also be proved that this expression is the proved. If I close all of them simultaneously, then also this expression is proved with 1, and because both inputs are 0. Now moving to our second circuit, that is this one. In this De Morgan's law, this expression we would be proving as f is equals to a naught multiplied by b plus c naught multiplied by d. Now the inputs of b and d are directly connected with the AND gate. So whatever the connection would be here, this will directly be implemented at the input of AND gate. But for the A and C, whatever the input would be, it will be inverted to inverted, and it would produce as the output of input as AND gate. So if all of them are 1, this 1 would connect it into the will pass from the NOT gate and will be produced as 0. So if any one of the input of the AND gate is 0, it will result in low logic. So both of the circuits over here are producing low logic. But if we close this. Okay, so these both are closed, so this will reduce the high logic. This proves that any one of them is for the zero of the OR gates are zero, and this output a D or B is 1, it will result in the positive of it. So why is it? Because 0 converts from OR gate and produces as a 0, 1, a high logic, and this high logic is present over here. So when this expression is also 1, this results in the both the expression as 1, which results in the formation of a positive 1 here. So by this our equation of Boolean expression, a Boolean expression is also proved. Now we would be going to Boolean function, simple Boolean function, by which first we will be watching a simple Boolean function. By that watching that Boolean function, we would be able to interpret the functionality and the function of de Morgan's law. So we would be going to this Boolean expression. What is it? Here, this is the Boolean expression over here. I have implemented this circuit with logic gates as well as with logic probes and toggles, and as well as with the push buttons and battery. So first of all, okay, here I hope you can all see. This is our circuit, both of the circuits. And this in this circuit has a equation of x plus z dot y is equal to f1. Now, if by this equation we can imply if as this is an OR gate, that if any of the output of this x is 1, this result in the positive 1 at the OR gate. And if any value time that x dot y dot z is 1, this result in the 1 as 1 as well. Like over here we have on both of the x and y, it resulted in the positive 1. But if any of them was sorry, any one of them was closed, it results in the closure of this function as well. This can also be seen over here by this, and you can see that this is a proved. So now we would be moving ahead to De Morgan's law. Sorry. I've already implemented the circuit so that we would save our time and the results could be explained more efficiently and more relaxedly, because these are. So here I have implemented my De Morgan's for both of the equations of them. So first in the equation it was x dot x. Oh, sorry for the inconvenience. For the first equation of De Morgan's law, we have x comma x dot y dot x dot x cross y the dot not is equals to 1. So if I created the whole assimilation process and everything over here, so we can simply check it from